expectation or conditional expected value. And so now, so the motivation is, well, this is all analogous of the discrete random variable, the concept from the discrete random variables, but here it's maybe more useful, even more useful than for discrete random variables. So what we did so far, we looked at the examples of joint density and marginal densities. So marginal densities. And so it's easy to explain by examples. So we have an example. So when the density is it's just written as something like that. So 3x, right? And so this is a value of the density. Right? So in you can think about it as a probability to be at the point xy. So here it depends on x, but in principle, this is a function of x and y. Just in this specific example, it happened to be that this density doesn't depend on y. And so, but it's the probability to be in a small area. It's so so that this is a probability that x and y belongs to the area to the area which is given by it's a small rectangle with the coordinates x, y. So x plus dx y, right? And so here's y, x, y plus dy, and this is x plus dx, y plus dy. And so probability to be in this small area divided by the in this small region, divided by the area of this region. So this is a meaning of this thing. And in our case, it happens to be equal to 3x, but not everywhere in the region where 0 is smaller than y, smaller than x, and smaller than 1, and 0 otherwise. And so this region, so we have a region in which the density is not 0, and this is a called a range of this pair of this random vector. So this pair of random variables x and y. And so it's a couple of two random variables, so it's a vector. And so now all it's also called support of the density. And so the area where the density is not equal to 0. Right? So support of the density. And so now to visualize it, it's always useful to draw a picture of the things when we deal with two random variables. If it's three random variables, it's difficult to draw a picture, but for two random variables, it's easy and so why not to draw it So now when we draw it, we will see we saw that the range is given by this inequality, and we draw this inequality, we find that this is this triangle. So yeah, why it doesn't allow me? Yeah. So this is triangle, right? So it's everywhere inside this triangle. It's equal. The density is equal to 3x. Outside of this triangle, it's equal to 0. So well, we want to calculate the probability to be in some specific area. We'll need first of all to take the intersection of this area with the range with this triangle. And so and after that we saw that we can also defined the marginal density. So if we're interested in just one random variable, then we can just write down the probability of one random variable, the density of the one random variable. Right? So this is the density of one random variable, and if we want to figure out what's the density, we just integrate the joint density. Right? So we integrate the joint density. Here it's 3x. Right? And so we integrate overall possible values of y. Right? So it's actually integration over dy. Right? So pictorially, it means that we fix some x. Right? So we kind of want to figure out what's the probability that the what's the probability that the random variable x is around this small x. Right? So what's the density at this particular point? So probability to be in a small interval around the x divided by the length of this interval. Right? And to figure out, we just integrate over this line. So overall possible values of y. But integration over all possible values of y, it's well, it's almost everywhere. It's equal. It's many places where density is equal to 0. So in fact, we'll need to integrate only over this over this interval. And so the integration goes from y is equal to 0, so which corresponds to this point A here, to y is equal to this point, right? So and at this point y is equal to x. So we will get this integral. So if we integrate it, we will get that this is equal to okay, so kind of, so here's a kind of a easy kind of the easy to make a mistake kind of. So we're integrating over y, so kind of it's 3xy. So it's actually 3xy antiderivative from 0 to x, not 3x squared divided by 2, but 3xy. So it's equal to 3x squared. So this is a marginal density. This is we learned before. And similarly, if we want to figure out what's the marginal density of y, then it will be also integral of 3x over density, but integration over dx. And so we integrating all values of x. So we fixed y. So fixed y, and want to figure out what's the probability that the random variable y is near this value y small. So we'll need to take all points on this line and sum together the probabilities to be on this point or on this line. So there is integration. Okay, so kind of in this case it's again 3x over dx, but important thing to figure out what's the bounds of the integration, and you'll see that in this case the x can change from y kind of, right? So this is x, which corresponds to this fixed value of y. So from y and to 1. So this is kind of, this is the bounds of the integration. So the only thing that we need to figure out here. And if we integrate this thing, so this is a kind of easy here, 3x squared divided by 2 from y to 1. So it will be equal kind of after some calculations. So you will get it with equal 3/2 of, even without any calculation, so 1 minus y squared. Right? So kind of this is what we learned previous class or previous lesson. So this is previous lesson, and if you know the marginal density, joint density, then it's possible to calculate many probabilities using this. So in particular, we looked at the say conditional probability. So kind of even conditional probability can be calculated without any conditional density sometimes. It depends on what's the conditional probability. So we looked at the conditional probability, which was probability that x plus y smaller than 1, given that y is greater or equal, or greater maybe kind of than 1, maybe greater or equal than 1/4, right? So smaller or smaller than equal, greater or greater or equal doesn't matter much in this context, because they are continuous random variables, so equality holds with probability 0, so it's the same whether y is greater or equal than 1/4 or equal 1/4, right? So, and well, it was easy to calculate, because by definition we could write that this is x plus y, so it's just the definition of a conditional probability, which means that you need to look at both x plus y equal to 1 and y is equal to 1/4, y is greater than 1/4. Right? So this kind of comma here means and, right? So both conditions must hold, and divided by the probability of the condition, and everything can be calculated in this case. So, so pictorially, graphically, it means that you are looking at the, again, so you're looking at the range here. So this is the range. So this is the range here, and look at the areas. So in the numerator, you have the x plus y smaller than 1 and y is greater than 1/4. So x plus 1 smaller than 1, so you'll need a kind of line x plus y equal to 1. So this is x plus y equal to 1. And so you just need, we would just want to draw what's the region here in the numerator, probability of what region we're calculating. So it's below this line, so x plus y is smaller than 1, and it's above the line y is equal to 1/4. So it's y, this is x. So also we have this line. So it's above this line. So, okay, so it's clear, so that we actually, the numerator here talks about this, maybe big, I don't know, maybe kind of, let me just do it. So we are talking about this region. So this is a kind of a probability of this region we can calculate. We calculated it this last time using the joint probability. We just need to take the joint density and integrate over this triangle. So it may be not so easy, but kind of doable. So now if you look at the probability that y is smaller than, sorry, here is great, should be greater or equal. Okay, so it should be also, it's the probability of the condition. So it should be greater than or equal than 1/4. It is like here, like here, like here. And so now kind of you think about what you're calculating here. So, well, you can think about in two ways. In principle, you can also look at this as the region, right? And say, okay, so what's the region here? Probability that y is greater than 1/4. You could just look at this is region, right? So it's everything above the line y is equal to 1/4, but you also need to intersect it with the range. So in principle, you can take the joint density and integrate it over this region, and you'll get the probability of whatever is in the denominator, right? But since it is about the one random variable, you could also calculate, we can also calculate it using the marginal density. And so the whole, both the numerator and denominator can be calculated using the joint density. Well, and for the denominator, we can also write it down using marginal density. So small shortcut, we can make a shortcut using the marginal density. Yeah, so in general, you would get something like that. Right? So if you write it accurately, then you'll get something like that. This is something like this thing. So you'll get the integral here will be double integral, right? And you'll need to write double integral. Well, if you want to calculate it, so this integral over this triangle, over this green triangle, should be written as a repeated integral. Right? And so in this particular case, it was easier to integrate first over x, inner integral over x, and outer integral over y. Right? It was easier to do it this way. Right? So because in this case, y is changing from 1/4 to 1/2. Right? So here's kind of a change. So from 1/4 to 1/2, this is outer integral. Right? And the inner integral, if you look what happens when y is fixed, so inner integral happens when you kind of fix the value of the outer variable, and look at the integration over inner variable. Right? So in this case, kind of the integration is over this small line, over small interval here. Right? And so if you figure out, okay, so this is a fixed y, so what's the change in x here? You'll see that this is from x to sorry, not from x, from y, right? So from x equal to y, so you need to express, you cannot integrate over x. You integrate over x, but the bounds of integration should be in terms of the outer variable, in terms of the y. So from y to 1 minus y, here you write what's the joint density, 3x. Right? So, and this is, you set it up where this is the set up integral for this probability. So, well, kind of looks complicated, but it's straightforward. Right? So just want to figure out what's the integral of this triangle. So we'll need to do it as a repeated integral. So, well, kind of it's easy to do it in this way. Otherwise, we would need to have two integrals, right? So two different pieces of the integral. So we did it again, so the previous lecture, so well, kind of small repetition of this. Because now about y again, so you could, so for the denominator, you could repeat it with kind of just take the integral of this large triangle with borders in red. And so it also could be a double integral. But since we already calculated what's the marginal density, so we can write it simpler. We can write it that this is equal to the integral from okay, so from here, so it's probability over y, sorry. So okay, so it's probability over y, right? So right? Here we'll write a marginal density for y. Okay, so the marginal density for y was 3/2 1 minus y squared. Yeah, so this is a marginal density for y. The only thing to figure out kind of what's the bounds. So you're integrating over y. So kind of this is a kind of something that maybe I skipped when I wrote. Kind of when we wrote this marginal densities, we also in principle need to write down what's the range of them. Well, kind of in this case it was something like a simple. So if y between 0 and 1 and 0 otherwise. And the same was for x. So this is 3x squared if x belongs 0 to 1 and 0 otherwise. And so range of this marginal density is from 0 to 1. So kind of it's from 0 to 1, but we're calculating, okay, so we're calculating what's the probability here. So it corresponds to every point where y is greater than 1/4. So it corresponds to this range from 1/4 to 1. So we write here is from 1/4 and to upper limit of the range to 1. So the support of the marginal densities from 0 to 1, but since you're calculating probability that y is greater than 1/4, you integrate it from 1/4 to upper limit of the range, to 1. And so, and after that there was a kind of, so this is kind of was a, after that was a calculation, right? And well, it was a straightforward calculation. So just kind of once you set up this integrated, you're integrating this kind of, well, using the rules of the calculus, and eventually it gives you something like uh, 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 so this integral, turns out to be, well, it's a hard integration, but it turns out that this is equal to 3 divided by 32. And this integral turns out that this is equal to 81 divided by 128. So altogether, kind of, if you calculate it, it gives you it gives you 4 divided by 27. And so again, so well, this is maybe kind of, well, it's a calculation. It is possible to make a mistake, but kind of it's useful to understand that kind of how we set up these integrals, right? So kind of the first things, draw a picture, figure out that the numerator corresponds to the region which is given by this green triangle, that numerator, it corresponds to the region given by this triangle with the red border, and in principle the kind of the and the denominator is easy to calculate if you already know the marginal density, and because it's only about one variable. Okay, so this is how we use the joint density and marginal density. And just to calculate the probability if the regions we are interested in is like a, well, kind of, it's a regions, right? So it's not lines, it's something like green triangle here or a triangle with a red border. So such that it has a positive area, right? So we can expect that we can integrate and get something positive. So now the problem arises when you look at it something like that. So if you look at the probability, the conditional probability that x plus y is smaller than 1, but the condition on that y is equal to 1/4. So now kind of, so what's the difference here? So again, so let's repeat this picture. Okay, so this is the picture. Again, so this is the range of this. This is the range of this the joint density. So we're using the same joint density. Now, in this particular case, what we are interested in is to know what's the probability that x plus y is smaller than 1, given that y is equal to 1/4. So we know that y should be fixed at 1/4. So here's 1/2, here's 1/4. So the condition gives that we are on this line. And so, and we are interested to know what's the probability that that x plus y is smaller than 1. So now kind of again, so here's the line x plus y equal to 1. So x plus y equal smaller than 1 is below this line. So we're interested in the probability that we are here on this portion of this interval. So from the condition that we know that we are with this horizontal line from here to here, this is our condition. So we're interested to know what's the probability that, well, given that we are on this red line, so what's the probability that we are in here on this green interval? And so the previous formula doesn't work, because in this case what we'll have is probability that x plus y are smaller than 1 and y is equal to 1/4 divided by probability that y is equal to 1/4. But this not helpful, because say looking at the denominator, you see that's probability that y is equal to 1/4. Okay, so this probability is equal to 0. Right? So kind of right. So kind of it's first of all obvious because it's continuous random variable. On the other hand, if you want to kind of to calculate it using the marginal density, well, you can. It will be integral from 1/4 to 1/4. It's kind of over dy of 3x, so it's equal to 0. Kind of also can think about this way. Right? Right. So this probability is equal to 0. Probability of the numerator is also equal to 0. Right. So okay, we cannot divide 0 by 0. So now the question is how we can calculate it. And this is exactly for these questions when we have a concept of a conditional density. Right. So to kind of see how conditional density works here. So suppose that we know what's the density of a random variable x, right? So given y. Right? So first of all, we write that this is probability that x plus y smaller than 1, given that y is equal to 1/4. Right? So this probability is equal to probability that if we know that y is equal to 1/4, right? And if we know that the probability is equal to 1/4, then we can write that this is a kind of x plus 1/4 smaller than 1, given that y is equal to 1/4. Right? So here we can write that this is equal to the probability that x is smaller than 3/4, given that y is equal to 1/4. So kind of okay. So this is the first thing that we can do. And the next thing is to realize that in this case, this is something about the probability of x, only the probability of a random variable x. So we could write it down, okay, so we can write it down as the density of x, right, over x and integrate. So it's a probability that x is smaller than 3/4, so 3/4, right, and kind of to something here, right? So now we need to understand kind of, so what's the density here and what's the lower bound. Now again, so this is more clear to understand, clear to see if you look at the pictures. It's easy to see. So we fixed that this is okay. So this is equal to y is equal to 1/4, right? So, and we want to figure out what that's we are in this interval. All right. So now, okay. So this means that we'll need to integrate over this interval. So this is from 1/4 and this is 3/4. So okay, so the lower bound is 1/4. Right? So because, well, kind of the density here is equal to 0. Okay, so now kind of, so we're integrating from 1/4 to 3/4, but what's the density we are integrating? It's not a marginal density, because in kind of well, kind of the marginal density is just x if we don't know anything about y, and this is not the joint density, because, well, it's just about one random variable, about x. So it turns out that in this case we'll need to use the conditional density. So we'll need to have a x plus y, and here's x given y is equal to 1/4. So this is kind of, so, well, this is is a similar to the questions that we had about the universities, right? So if we have two universities before, right, in our example with two universities, we have a y and x, right? So, and there was 1 0 1 2, here's 1 0, so maybe here's y better and here's x, 0 1 2, and here we had the probabilities 1/9, 1/9, so 1/9, 1/9, here's 2/9, 2/9, 2/9, right? And here's 0 0 0. Right? And if we ask the question, what's the probability that, say, something like that? So what's the probability that x plus y is smaller than 1, given that y is equal to 0, right? So in this case, what we did exactly the same thing like before, right? So we would, so smaller than equal than y, we would write that this is equal to the probability that it's x smaller than 1, because y is equal to 0, right? Given that y is equal to 0. So after that we said, okay, so what it means? So we are looking at the row with y is equal to 0, at this row. Right? And we want to figure out what's the probability that x is smaller than equal than 1. So we'll need to calculate the probability of these two cells. But we don't simply add 1/9 plus 2/9. We need to go from these probabilities, from the joint PMF to conditional PMF. So in this case, what we would do, we'd say, okay, so we'll need to write that in this row, the probabilities in this specific row, right, with the row that y is equal to 0, the conditional probabilities of x, so f of x, given that y is equal to 0, so these probabilities are for 0 is equal to 1/9 divided by the marginal probability of 0 divided by the sum of all these numbers, 1/9, 2/9, and 1/9, divided by 4/9. And here we would have that this is 2/9 divided by 4/9, and here we'll have 1/9 also divided by 4/9. So so this is 1/4, this is 1/2, and this is 1/4 again. And we would like to calculate the sum of 1/4 plus 2/9, right? So we would have that this probability was equal to 1/4 plus 1/2. Right? So this is how we did it in discrete case. So we are doing exactly the same thing in this continuous probability case, by looking at the integral, right, from the range, kind of, so on the range where the random variable x, is smaller than or equal than 3/4, so from 3/4, but it's also kind of, it should be greater than 1/4, right? And integrating not on the joint density, but the conditional density. And so how we can define this conditional density? So we define it by analogy from what we did in the discrete case. And so in the discrete case, what we did, we looked at the joint probabilities, which was 1/9, 2/9, 1/9, 2/9 here, right, 1/9, and divided by the marginal PMF, divided by 1/4, by the sum of all of them. Right? So we are doing it exactly the same thing here. So we define that f of x given y of x given y, it's equal to the joint density f of x y divided by the marginal density. Right? So, and what's the marginal density here? It's f of right? So by the marginal density of the condition. Right? So by the again, so here we divided by the sum. So in this example, we divided by the sum of the row. Right? So for the value of 0 here, for the value when y is equal to 0. So here we are also divided by f of y of y. Right? So this is kind of the formula that we want to use, and in application to our specific example, we're saying that this is f of x, y evaluated at x, and y should be equal to 1/4, right? So we put here 1/4. So just equal to f of x, here is 1/4, divided by the, and this is the joint density, divided by the marginal density, which is f of y of 1/4. Again, so this is it goes exact analogy of the discrete case. So we are integrating all this line. So in integrating using the conditional density is just the joint density but normalized, divided by the integral over all values on this line when y is equal to 1/4, divided by the, in other words, divided by the marginal density. Right? Okay, so maybe kind of it's kind of could look complicated, but it's again an exact analogy of what's going in the discrete case. And if you look at the discrete case, if you kind of calculate in the discrete case, we cannot use 1/9, 2/9, 1/9. In this case, because it's not really a probability mass function, it doesn't sum to 1. We'll need to normalize it, and to normalize it, we divide by the sum of all these probabilities. Because we already know that we in this row, so we'll need to update the probabilities proportionately. So we'll need to increase them. And if we increase it proportionally, this means we're dividing by the sum of all values in this specific row. Same thing that we are doing here. We are looking at this formula, and we are saying, so to calculate the conditional, kind of the density of x, which we will use in our calculation, we'll need to take the joint density, but normalize it. So increase them, because we already know them this line. And so kind of how we can normalize it, we divide it by the integral of this line, and this integral is equal to the marginal density. Okay, so now kind of this formula kind of we can write it in terms of the formula. So the joint density in this case, it turns out that it's still equal to 3x. It doesn't depend on y, so it's 3x. And so kind of the numerator here is 3x, and in the denominator we have previously calculated the marginal density. So 3/2, 1 minus, and here should be y squared. So we kind of put here 1/4 squared. So, okay, so this will be equal to something. So let me see if I wrote what it is equal for. No, didn't calculate it, but yeah, so kind of, okay, so it's equal to something, and after that, yes, it's 16/15 or something like that. So we can calculate it here. So it's equal to 2x, and here's 16, 15 16th. So it's equal to 32 divided by 15x. So this is a conditional density of x evaluated at y is equal to 1/4. It's evaluated at y is equal to 1/4. And so to calculate, so now to calculate this probability that x is smaller than 3/4, given that y is equal to 1/4. And so it's integral from 1/4 to 3/4 with conditional density, which we just calculated, 32 divided by 15x dx. So, and if you calculate it, it turns out that this is equal to it's equal to 8/15. So questions about this? So this is example. So it turns out that this is kind of sometimes hard for many students to understand what's going on here, but it's kind of should be more or less simple, kind of. So now, so this is kind of was example, and this was something like just a motivation for why conditional density is useful, right? So now, kind of, what's the definition, right? So now, kind of okay, 45 minutes, we come to the definition of a conditional density. So what's the conditional density? Conditional density. Density, so f of x given y of x, y. So now kind of, well, kind of by definition, it's simply the ratio when you divide the joint density of x, y, divide by the marginal density of y. So that's it, kind of. Okay, so this is a conditional density, and also kind of they both kind of again. So we can be conditional density of x given that you know y, that y is equal to this y small, and also you can also have conditional density of y given that you know something about x. Right? So in this case, I write it y given x small. They in general not equal to each other, and it's equal to, okay, same joint density, but now you're normalizing it by dividing by the sum of its joint density over all y's. Okay? So you divide it by of f of x and y. So f of x of x. It might be instructive if you write with ratios using the definition of a marginal density. So you can also write it both this expression and this expression. You can write it this way. So you can write x, y of x, y. And here, instead of writing the marginal density, you just write the definition of what is it. So it's integral from over range of x, sorry, over range of y. Here's f of x, y, over dy. Right? Again, so the picture that should be kept in mind is that you have a joint density, right? Something like maybe kind of like in the previous example, something like that. So you have a joint density, and you want to figure out what's the probability distribution, what's the probability density of y given that x is fixed. So in this kind of here, in this form of a fixed x, and you want to figure out what's the distribution of y. So it's on this line, and so you just take the joint density on this line and divide it by the sum of all this joint density over all possible values of y. So divided by the integral of this joint density over this line. So which is equal kind of this is this integral, this is equal to this f of x of x. So let us kind of to make sure kind of that it's kind of that it is clear, what the definition is clear, let us calculate it again, the marginal density in this specific example. But in the previous case, we calculated what was probability of x given y, right? So y was equal to 1/4, and we calculated what's the probability density of x, conditional probability density of x. Now, so let us look at the example. So the same example, maybe, and just let us repeat the calculations. So for x, y, but more generally, kind of f of x of y, for the general y, not only for 1/4, but for the general y. Right? So, and also what's the y of x given y given x. Right? So suppose you're given x, and what's the probability distribution of y. So again, in the same example. So so let us do it again. And so again, so in this case, it's very useful to draw pictures. And so this is the same picture, we're repeating it again, but kind of, so it's useful. And so this is our picture. So we have a, just repeat, we have a f of xy is equal to 3x, then 0 smaller than y, smaller than x, smaller than 1, and 0 otherwise. So from xy. Now, okay, so this calculation we did before, just kind of let us formalize it. So f of x given y of xy, it's equal to definition f of x y of xy divided by f of fy of y. And so it's equal to 3x divided by, we calculated sometime before that this is equal to 3/2 1 minus y squared. Right? So in the beginning of this lecture. But that's not the answer, not the whole answer. So this is, if you calculate it and give it to me, this is not right, not really kind of enough to specify kind of answer. The problem is that you also need to say what's the range kind of where this is valid. Right? And it turns out that, well, kind of arrange it, well, kind of you specify that y, so here's some fixed value of y. So, and you fixed x, you fixed y, and now you're thinking about what's the distribution of x. So x is 0 everywhere outside of this. So the density is 0 everywhere outside of this yellow triangle. Right? So now if you specify that the value of y is equal to this specific y, then we are living on this interval. So where kind of is, what's the bounds of this interval? What's kind of the range of this distribution. Okay, so this is from x, it's from x equal to y to 1. Okay? So this formula only valid if x is greater than y and smaller than 1. So again, you can think about like y like in the previous example, something fixed like 1/4. And so this formula would say that this is from 1/4 to 1. So this density is true only from 1/4 to 1, right? And 0 otherwise. So now this is a valid answer, kind of, right? So because you think kind of it's y is equal to something, and x is equal to 0 everywhere except on this interval, except when between y and 1. Now, what about kind of the other one? So what about f of y given x? So maybe here should be kind of in the previous definition, I think also I need to put it y given x. So this line here is given, right? So its formula was almost exactly the same, x of y, x, y divided by f x of x. So here's 3x, right? And here was, okay, so what here was marginal density of x. And again, so in the beginning of this lecture, we calculated it was equal to, well, we can go up and see what was it. So we calculated what here was the calculation of this marginal density. So we calculated that was a 3x squared. So divided by 3x squared. So here it simplifies, it's equal to 1 divided by x. But again, we'll need to say what's the region in which it's equal to 1 over x. So now we have if x is fixed, and we are thinking about the distribution of a random variable y. So it can be on this line only. So its ranges, it can be only between, it have a positive density only from when it is between 0 and this value, right, which is equal to x. So if y is greater than 0 and smaller than x, then 0 otherwise. Okay, so this is again kind of complete answer. And so you fix x and say what's the distribution of y, what's the kind of probability density of y given that the value of x is equal to this specific value x small. Well, it's equal to 1 divided by x. The density is equal to 1 divided by x. But only if y small is between 0 and x. Okay. So again, so here's a case. So we can give an example for this case. So example, if x is equal to 1/3, then f of y x of y 1/3. So if we know that x is equal to 1/3, then in this case it's equal to 1 divided by 1/3. So 1 divided by 1/3. If, so which is 3, right? If 0 smaller than y, smaller than 1/3, right? And 0 otherwise. In the picture, this would look like kind of that you fixed x is equal to 1/3, and looking what's kind of the possible values for y. And possible values for y is between 0 and 1/3, right? And the density on this interval is equal to 3. Okay, so it's a constant density, it doesn't depend on y, so it's uniform distribution on this subinterval. Okay, so well, hopefully this is a more or less clear, right? So kind of, so to summarize it, that the joint density, you use joint density. Well, if you want to calculate the probability that two random variables in some region, some big region here, so like so you select some region like here. So what's if you want to figure out what's the probability to be in some region like that, well, you join density. Marginal density you use if the region is very specific, if it just depends on one random variable. And the conditional density, you use the conditional density if you specify some specific value of one random variable. So now kind of the other random variables, so the couple of these random variables lives on the line, on the horizontal or vertical line, and you'll need to figure out the probabilities that kind of it's somewhere in the inner interval on this horizontal or vertical line. Okay. Right, so okay, so let's make a break here, small break here, and we'll continue later. Right, so continue in 5 minutes. All right. So maybe let's restart. Um, so now maybe kind of a couple of words about why kind of it's in some sense applicable in practice. And so the reason is that you often have a couple of random variables, so y and x. Right? So you have a y and x, and often you have a problem of a prediction of y given x. So prediction uh, of y given x. So of y given x. So kind of some example would be kind of say you have a economic kind of some economic model, and you have y in this model. Y is say income, or maybe logarithm of income. So it says simply income here, and x is say age. So maybe experience of a worker. So now you look at the general population, and you in general have a distribution of y and x. So if you took a random person from this distribution, you'll have a usually pair of, well, what's the experience of this specific worker and what's the incomes of a worker. Right? So we have a joint distribution. And so now in usual question that arises, well, kind of what's how y changes when experience grows, right? And in this case, you can have a say x is kind of several values of x. So if you have a value of x is equal to 0, well, you can see what's the distribution. So you look at the subpopulation of people who have a experience equal to 0. So just people who enters the job market and have absolutely no kind of prior experience. Right? And in this case, you will you'll observe some distribution of y. Kind of you can write it down and kind of approximate it by a density. So you'll get something like a picture like that. So some kind of a density of y given x is equal to 0. Well, kind of in what we talked before, that is just f of y given x evaluated at y given that x is equal to 0. And so kind of this is a function of y, so function of income. And so now if you look at x is equal to some greater value, so 1, so if you measure something in years, right? So well, you have a different picture here. Right? You will have something like that. Maybe kind of, since experience is larger, then in general you have that the whole distribution moved a little bit to the right. Right? So kind of the income of the people with have 1 year experience are larger than the, in general, kind of larger than the income of the people who have 0 years experience, but not necessarily true. So you can find one person with 0 years of experience and which has a larger income than the person with 1 year of experience. So, well, it's a distribution kind of a distribution moves to the right. And x is equal to 2. Well, you have another kind of distribution. So in general, kind of even larger than that. So kind of you can see here, so that's kind of the conditional density. How this conditional density, well, it's a density, it's a distribution, but it changes for x, right? So for x is equal to 0, it's different than for x is equal to 1, it's different than for the x is equal to 2, and so on. That is equal to x is equal to 2. All right, so this is useful information, but in general, kind of people are interested not in the kind of just distribution, they're interested in just some kind of numbers. Right? So if you have that the experience is equal to 1, right? So what's your best prediction about? So you choose a random person, right? So and you know that the experience of this person is equal to 1 year. So what's your best prediction about the income of this person? Okay, so well, with this is kind of one specific problem, but you can see that can happen in many situations. Okay, so right, so you know the conditional density. Okay, so the density of the distribution of the income given the experience is equal to some specific value, for example, to 1. So what's the best prediction, right? So the best that you can do is use the expected value relative to this conditional distribution, right? Relative to know that the conditional distribution is well equal to conditional density is equal to this specific function. Right? So, and this thing is called conditional expectation. Conditional expectation. So it means expectation which depends on some kind of a value of some one of these random variables. Conditional expectation of y given that you know that x is equal to some specific value. And then you can see that this is kind of a very natural thing to use in a prediction of y given that you know the x. So this is a kind of motivation for using the conditional expectation. So in some sense, it's also a motivation for why to look at the conditional densities, but kind of, well, conditional expectation. In some sense, kind of in several cases, this is the optimal thing that you can do about the prediction. So conditional expectation. So by definition, so conditional expectation of a random variable y given that x is equal to x small, it's just the okay, so it's the integral of y with with respect to the f of y, sorry, respect to f of y given x, conditional density of y given x, y, and here's x. And you integrate it over dy. Okay, so now integral of what to what? Well, in principle, you will need to the range of a random variable y, so kind of maybe kind of write it here. So range of y given x. I could also write from minus infinity to infinity, but you need to integrate over all values of y where this density is not 0. Okay, so this is a conditional expectation of y given x. Of course, you can define also conditional expectation of x given y. It's just kind of you change where in every place here y to x and x to y, and you'll get the kind of the same thing. But more generally, you can also define expectation of any function of y. So f of y, x given x, just equal to integral of f of y small. Okay, maybe kind of let me kind of not to clash the notation, let me call it g, functions g, because we use f as a standard notation for the density. So let me call it g here. G of y, here's density f of a given x, y given x, dy. Gain range of y given x. So, well, kind of in this example, kind of we didn't specify exactly what's the formulas here, but it would say kind of if you have x equal to 1, just kind of look at the corresponding conditional density and integrate using this conditional density. All right. Now, so that's it. Kind of let's do this calculation. So let's calculate it in an example. Okay, so now let us look at our previous example. So then, okay, f of x of y, xy is equal to 3x, 0 smaller than y, smaller than x, smaller than 1, and 0 otherwise. And again, so let us draw a picture here. So it's always kind of useful to draw a picture in these problems. Right. So y, x. And now kind of let us calculate both the expectation of x, given that y is equal to y small, and expectation of y, that given that x is equal to x small. So let us ask the question about this thing. So now how we can do it. So let us look at expectation of x given that y is equal to y small. So to do this, we'll need to know what's the density of the conditional density of x. So formula that here is x, and here should be the conditional density. And so now we calculated it before, and if you kind of look at this, so kind of y is fixed. So y is here is fixed, and we are looking at this thing. So it was equal to the joint density 3x divided by the marginal density of y. Marginal density of y was 3 divided by 2, 1 minus y squared. And you'll need to integrate it over dx in this case. So it will be a function of y. It will depend on y. So it's okay. But you'll need to integrate out fx. Next question is you integrating it, but you need to kind of be very careful. So integrating from what to what kind of. What's the range of integration? What's the bounds of integration? And it should be the range of x given that y is fixed at y. So y is fixed at y, so what's the range of x? Okay, so we're looking at, okay, so x can be only on this interval. So x can be changing only from this point to 1. So this point for a given y, this point is equal to y. Okay, so we're integrating it from y to 1. Okay, so that's it, kind of. And after that, well, you do this integration. Okay, so, well, kind of, let's slightly simplifying it, will equal to 2x. Here's 2x squared. Here will be 1 minus y squared dx. Here's y, and here's 1. So, okay, so 1 over y squared, it says it doesn't, so it's just kind of, it's a factor which doesn't depend on x, so you can take it outside. 1 minus y squared, 1 here will be integral from y to 1. Here we'll have a 2x squared dx. So it's equal to 1 divided by 1 minus y squared. Here's 2/3 x cubed evaluated from 1 to 1, so it's equal to 2/3. Here's 1 minus y cubed, 1 minus y squared. So right, so this is okay. So this is the expectation of x given that y is equal to y. You can plug in some specific y, and you'll get what's the expectation. So it's your best prediction about the x, right, given that you know what's the value of the y. Right, so again, so this is easy kind of. The only subtle points here, well, first of all, you need to calculate the conditional density. And the subtle point that you'll need to be very careful about the range of integration. Right. Now, what about expectation of y given x? Expectation of y, given that you know that x is equal to x small. And so, okay, so the same formula, except that, well, kind of in this case, you'll need to integrate y, right? And after that here, well, you should have a, so it's integral of y. Here should be the joint density of x, sorry, not joint, conditional density of y given x. So 3x divided by the marginal, density of x. And the marginal density of x, well, it was a 3x squared, right? Again, so in the beginning of this lecture, of the lecture. So we'll have here integral over dy. We take the expectation of y. Now, what's the bounds of the integration here? Right? If you look at this thing, so you again look at this picture, and you're saying right now we fixed x. Okay, so we fixed x, and for this specific x, what's the possible values of y? Okay, so well, it's from 0. So the possible values of y for a fixed x is from 0 to x. Okay, so only in these cases where joint density is positive. So only in these cases you are here. You kind of only if you have if you are on this line, on this interval, the joint density is positive. Nice. So okay, so this integral should be from 0 to x. Okay, so what it is? So integral from 0 to x, y 1 divided by x dy. Again, so we can take 1x outside. So here's 0 from x, y dy. So it's equal to 1 divided by x. Here's y squared divided by 2 from 0 to x. So it should be equal. So here's x squared, 1x, x squared divided by 2. So it's equal to x squared divided by 4. Sorry, no. Okay, so 1x here. 1x, x. Right, 1x, x squared divided by 2. So altogether we'll get that this is equal to x divided by 2. Let me check it because I'm, yeah, x divided by 2. All right, so this is the calculation for the conditional expectation of y given that you'll know the x. Right? That's equal to x divided by 2. So kind of you think about this, well, so you learn that the random variable of x is equal to x. So what's your best prediction about y? It turns out that in this case, it's exactly kind of in the middle of this line. So it's equal to x divided by 2. So the best prediction here, so would be here, so x divided by 2. Okay. Now, so maybe kind of, well, just a reminder. So in this case, well, kind of it's interesting kind of, so think that to reminder interesting thing to recall that we also have something which is called the law of iterated expectation. Just kind of, this is just a reminder, and we looked at this law in the case when we have a discrete random variable, and the law said something like that, that expectation of x, say, was equal to expectation of expected value of x given y, right? Like that. So the meaning of was well kind of, so you can calculate the expectation of x for every value of y, right? And so, and well, this will be a random variable which depends on y. So you can think about as a function, this is a function of y. And so y have also some kind of a distribution, so we can calculate the expectation with respect to this distribution. And the law of iterated expectation says that you have this equality holds. So, well, let's check that this is true in this particular example. Okay, so let's check that this is indeed true. And well, kind of a corresponding also will have the expectation of y is equal to expectation of e of y given x. Yes, so this is something like that one. And so kind of in the practical terms, so we can calculate in practical terms, it means kind of something like that. So you're looking at in this picture and you're saying, all right, so suppose that I know that x is equal to 0 for 0 years of experience, the expected value of the income is equal to some specific value. Well, for x is equal to 1, for 1 year of experience, I know that the the expected value of income is equal to some other value, kind of, right? So here's something like, well, okay, so this is e of x given 0. Here's something like e of x given 1. Here's e of x given here e of y given x is equal to 0, e of y given that x is equal to 1, here's e of y given that x is equal to 2. And so now, well, kind of what's so you know the conditional expectation of income given in each experience group. So now what's the overall expected income? Right? So, well, you can average overall over distribution of x in this case. And after you average over the distribution of x, you will find out that what's the overall expected value of the income. So now kind of this is the meaning of this law of iterated expectation. Well, in our case, kind of, okay, so let's calculate what's the expectation of expected value of x given of y. So, okay, so what's the expectation of x given y, right? So now we are going here, so we calculated it, so it's calculated here as expectation of x, that given that y is equal to y small, it's equal to this thing, right? So it's 2/3 1 minus y cubed divided 1 minus y squared. So it's equal to 1 2/3 1 minus y cubed divided by 1 minus y squared. So I just read it from this formula here. Okay, so now, okay, so what's about expectation of this quantity x given y? So we'll need to how we calculate it. And it's a function of y. So we write this function 2/3 1 minus y squared 1 minus y cubed divided 1 minus y squared. Well, and we calculate an expectation of this function of y. So we'll need to multiply it by the marginal density of y. Okay, so we'll need to multiply it by marginal density of y. What's the marginal density of y? Well, we calculated it again at the beginning of this lecture. It was a 3/2 1 minus y squared. So this is f of y of y. Right? And this is our function. Right? And we're integrating over range of y, so it's from 0 to 1. So and here's dy. Yeah, so telling us that this is cancel out, this is cancel out, this is cancel out, this is cancel out. Yeah, so it's equal to integral from 0 to 1, 1 minus y cube dy. Yeah, so right, so what is it? So it's y minus y fourth divided by 4, evaluated from 0 to 1, so it's equal to 1 minus 1/4, so it's equal to 3/4. So this is we calculated this thing. So now what about expectation of x? So just kind of what's if we calculate the expectation of x directly? So we want to check this equality holds. So now how we calculate it? Okay, so it's expectation of x. We're thinking how we can calculate it. Well, it's expectation of one single random variable, so 0, 1, x, and here's marginal. You should have a marginal density of x, so just density of x. So, and we know that this marginal density of x, okay, so what was that? So again, so going in the beginning of this lecture, so marginal density of x was equal to 3x squared. So it's equal to 3x squared. So dx. So this is equal to the integral from 0 to 1, 3x cubed dx. So it's equal to 3/4 x fourth from 0 to 1. So it's equal to 3/4. So okay, so this matches. So we checked that the law of iterated expectation holds in this specific example. All right, so now, okay. So this is basically it for today. So I understand that this is a very, well, it's a difficult topic. So most of the difficulties comes from the fact that you need to calculate this stuff. And so it's most of the difficulties is calculation. It's from the past experience, I know that this is tough for many students. So just the only thing that you can do is to solve many problems. So in homework, where I put the homework, I put in the homework many problems on this topic. The more problems that you do, the easier the easier it becomes. So from the point of view of the ideological point of view, it's not very difficult actually. It's much more difficult to just set up the integrals correctly and calculate the integrals correctly. All right. Okay, so the exam will be you just reminder that exam will be on the next Monday. Right? And so it mostly covers the topic. So it will cover the topics which includes this particular. So it covers also the conditional expectation, marginal expectation, joint expectation, and it will not cover multinomial distribution and multivariate Gaussian distribution from this chapter. So this is so maybe I'll send a little bit more information over the Zoom, but this is a first mention of the coming midterm exam. So if you have a question about this, well, you're welcome to ask the question. If no, well, so then that's it for today. Have a nice day.
Thank you, Professor.